Okay, thank you. We are back with our second talk this afternoon for the speaker. The speaker who is Martin Donati from the Institut Camille Jordan of the University Claude Bernard in Lyon. And Martin will talk about point vortex dynamics in bounded domains. Thank you very much, Martin. You can start anytime you want.
Thank you. Thank you very much for the presentation, and thank you for the invitation, Billy. So I will talk today about point vortex dynamics in the context of bounded domains. And obviously, this is joint work with my PhD advisor, Dragos Iftimir. Okay, so for a quick plan, I will start with a general introduction and then introduce the point vortex dynamics in the 2D Euler fluid, and then talk about what interests me, which is the problem of existence of solutions for bounded domains. Okay, so to start, I'd like to try to answer a question. Why would anyone study vortices? So I will not go into complicated explanation, but just try to convince you with some pictures. So here is a representation of the atmosphere around the Earth, and one could expect the air to flow naturally around the Earth, but that's not the case. You can see that it's turbulent. It spins around itself in what we call vortices, and thus this problem is interesting. It's also visible in the ocean. If you take a look at the currents in the ocean, you can see many vortices, many turbulent flow. And even here, unfortunately, a great example of a hurricane, which formed a couple of days ago in the ocean. Okay, what I'm interested in is the effect of the boundary. So here, another example of non-simply connected domain with complicated boundary and the vortices evolving inside this domain. Okay, so this problem is of interest, obviously. Let's say I've been convinced myself by those pictures. So a quick history of the point vortex dynamics. So it was studied first 1.5 centuries ago and introduced by Kirchhoff after Helmholtz and Kelvin study of the vorticity. And in 1993, Marco and Pulvirenti justified the model. And I'd like to mention also that recently Gelthauser and Romito extended it to the surface calgisostrophic flow, which is a nice model for the atmosphere, which once again extend the use of the point vortex model. Okay, so now let's start the maths. I recall the Euler equations in a bounded and simply connected domain with smooth boundary. So these are the equations with the usual boundary conditions that the velocity u must be tangent to the boundary. And we define the vorticity omega as the curl of u. So it describes how the fluid rotates around itself. And I recall the Biot-Savart law, which is that if you know the vorticity omega, then you can compute the velocity u, provided you know the green function g of your domain. Okay, so we have the vorticity equation, which is basically the Euler equations. When you took the curl of the first equation, you have the equation on the vorticity, which has the form of a transport equation. Okay, the vorticity transported by the velocity. The Biot-Savart law, of course, to reconstruct the velocity and an initial data. Okay, so this is the equation that I will work on first. In the case of multiply connected domains, though, the Biot-Savart law changes a bit because you have to add a term when you compute the inverse of the Laplacian. And these terms depends on the harmonic measures and the circulations. Okay, you don't have a unique solution when you inverse the Laplacian. You have a space of solution that depends on those circulations. So when you have a multiply connected domain, you have to add the circulations as an initial data and this term. However, this term will be always bounded in the context of this study. So as you will see, the fact that it's bounded means that it's actually not very important, at least to understand what happens here. Okay. So for this equation, we have existence of a global solution, at least in good context. So we have the Volidner theorem, for example, that if the initial data is smooth, then there is a smooth solution, global in time and unique. And we have the classical Udovich theorem that states that if the boundary is C11 and the vorticity is bounded, then there exists a unique bounded solution, globally time again. Okay, so these equations are have solutions and we can work with them. This is not a problem. So I want to say a quick word on the Green's function. So what I want to recall is that the Green's function always decomposes as such. Here, it's always the sum of the Green function of R2, which as we call is 1/2 pi ln of x minus y, and a smooth part, which I'll call gamma. Why is that? Of course, if you compute the Laplacian of the difference, g minus g of R2, then this equals 0 because it's a difference of Dirac masses in the same points. So this means that the rest is indeed a smooth function. Okay, so the singularity of the Green function is always the one of the Green's function of R2, the whole plane. And here we are also interested in the Robbins function, which is the smooth part of the Green function applied on the diagonal. Okay, so I want to make a quick drawing about, well, to illustrate this decomposition. So as we saw, the velocity is a convolution product of the Green's function and the vorticity. Okay, so what I want to understand is what is the influence of some vorticity placed in y on a point x, especially when you have a boundary. Okay, so we have a direct influence, which is represented by g of r2, xy, and you have an influence through the boundary of this vorticity placed in y. Okay, and this is exactly g of gamma of x, y. Okay, so this decomposition says simply that a vorticity placed in y has an influence that is the sum of the direct influence, g of r2, plus the sum of the influence through the boundary. Okay, when we have no boundary, this term equals 0. And what is the Robin function then? The Robin function is simply the self-influence of a point over itself through the boundary. Okay, this is tilde gamma of x. Okay, so now I hope we understand what this decomposition means. So the point vertex dynamics, his goal is to give sense to a solution when the initial vorticity is sum of Dirac masses. Okay, the Euler equation have no sense when we take such initial data. So we try to give sense to that. So the first assumption is that since the vorticity is transported by the velocity, we expect the sum of Dirac masses to remain a sum of Dirac masses. Okay, so this is our first assumption, that for all time, the vorticity is the sum of Dirac masses with the same masses that are fixed for all the rest of this presentation. The second assumption is the same, actually. We say that we want the vortices to be to move accordingly to the velocity field. Why is that? It's because the vorticity is transported by the velocity. Okay, so let us compute what this formula gives. So we compute via the Biot-Savart law the velocity in the point vertex Zi. And we use the decomposition of the Green's function to obtain that is the sum of this term plus, which is the gradient perp of the Green's function of R2, plus the smooth part, okay? But here we have the problem, because this term, which is of the form x perp minus x squared, is actually singular when x equals 0, okay? So we have a singularity in I equals j here. So how do we deal with that? Well, we say that since we have this perp, and this term is actually in some way of mean 0, around 0, then we choose to remove it simply, okay? We say this term must be 0. So we remove it, and we have our point vortex dynamics in simply connected domain at least, which says that the point vortices are moving according to the Biot-Savart law when we removed the singular parts. Okay, what remains for the case A equals J equals I, is the Robin's function, the self-influence of the point for the boundary, which is smooth, so we should not remove it. So let me mention that this is a Hamiltonian system. It is a gradient perp of the function. And so in the context of multiply connected domain, what you have to add is the same term that we had before, which again is a bounded term. So let's say it behaves correctly, nicely. Okay, so now we have introduced the point vortex dynamics. The question is, why is it valid? Because we made assumptions, we invented something. Why does it work? So we have many theorems and examples. I chose two that I think are relevant. The first one is the theorem of Marco and Pulverenti in 1993, which states that if you start with a smooth initial data that is supported in very small disks, which means it looks like a sum of Dirac masses, but it's smooth, then it remains up to technical conditions, supported in small disks that are moving, where the centers of the disk are moving according to the point vortex dynamics, at least in finite definite time. The second theorem is basically the converse. If you take a grid of point vortices that approximate a smooth initial data, then this grid of point vortices evolves and converges to the solution of the Euler equation. Again, if you take the right grid and the right conditions. Okay, what it means is that the point vortex dynamic is indeed a good approximation of the Euler equations, and the opposite and the converse. Okay, however, these two theorems have a strong limitation, which is that they require the point vortex dynamic to have a global solution. This is a problem that I have not mentioned yet, is that this global solution does not always exist. Okay, so this is what I will be interested in for the remaining of this speech. So the first result we have is a theorem of Marco and Pulverenti from 1984, which states that in the case of the whole plane, if there is no sum of masses that equals 0, then for almost every initial data, in the sense of the Lebesgue measure on R2 to the power n, then the point vortex dynamic has a global solution. Okay, so it's not always true. What is it not always true? It's because if you take a look at the point vortex dynamic, even in the whole plane with no boundary, if you have a collision, which means that Zi equals Zj for some j at some point, then we have the same problem that when we define the point vortex dynamics, this term makes no sense anymore. Okay, so the equations is not valid. And unfortunately, we have explicit examples for that. Okay, you can take 3 points and make the collapse in finite time. So this is sure that the point vortex dynamic has not always a solution, but what is true is that it have a solution, a global solution for almost every initial data in the sense of the Lebesgue measure. Okay, even if you have the conservation of the Hamiltonian, this is a Hamiltonian system, The fact is, since we don't know anything on the sign of the masses, this doesn't prevent collapse. Okay, if we know that all the masses have same sign, it's a different story, obviously. Let me mention quickly that for the HQG model, the same result has been proved very recently. It's a theorem from Godard-Cadillac. So he states that for the HQG model, also the point vortex system has a global solution, and he even removed the condition that the sum of every masses must be zero. Okay, all the sub-sums must not vanish, but not the total sum. Okay, so this extends the theorem of Marco and Pulvianti that we just saw. Now, what changes with the boundary, in the presence of boundary? So you have other terms. So this one, we said it is smooth, it's bounded, it's everything we want, so it doesn't cause any problem. But we have this term, the gradient perf of the Robbins function, which can become singular if a point hit the boundary. Okay. So once again, we are adding problems, but Marco and Pulvianti proved in 1984 that for the unit disk, precisely, then it's also true that for almost every initial data, the point vortex system has a global solution. And in that case, thanks to the boundary, there is even no restriction at all on the sum of the masses. Okay, can be whatever you want. So what I worked on and proved is that this theorem is also true if you take omega, a bounded domain, not necessarily simply connected, that is smooth enough. We say the boundary should be C2 alpha for some alpha. If you take this domain, the point vortex dynamic also have a solution for almost every initial data. Okay. So the two proofs of those theorems are very connected. It's really an extension of the theorem of the Marco-Pulvianti. And what I want to do in the remaining time is try to explain how the proof works. Okay, so what is the aim? The idea of Marco and Pulvianti was to measure the epsilon collapses. Okay, so I will introduce many things with the goal to compute the probability of the points getting close to each other, like with distance epsilon, or close to the boundary. Okay, with distance epsilon to the boundary. So the first step is to introduce an energy. Why do we need this? Because as we said, the Hamiltonian is not the good energy here, because it's preserved, but the singularity can appear and compensate themselves. Okay, so the idea of Marco was to introduce this energy, which looks like the Hamiltonian, but we remove the masses, so we have no sign problem, and we change the sign of the Robbins function, because the Robbins function goes to plus infinity when getting close to the boundary, while the Green's function goes to minus infinity when going to infinity. So Ding's function, when we take the right f here, which is an exponential for technical reasons, Ding's function goes to infinity if and only if there is a collapse, either 2 points colliding or more points colliding, or a point going to the boundary. Okay, so now this what I call energy, which is probably not a formal energy, but this threshold map phi measure efficiently if there is a collapse or not. The second step is to regularize the dynamics. Why we need to do that? We need to do that because to be able to compute, we need to know that there is a solution. Okay, so what we do is that we don't change the dynamics while points are far from each other, but when they get close at the scale epsilon, we make the dynamics smooth by force. Okay, so what Marco and Pulvianti did, they switched their ln, their logarithm function, with a threshold epsilon. They replaced it with something smooth. Okay, in all the formulas of the Green function. because they were working on the disk. They had explicit formulas with the logarithm appearing. So they cut the singularities of this logarithm, and now everything is smooth and we have global solution always. And it's changed only when this is ln exactly. It's changed only when you have an epsilon collapse. So what I did in the case of general domain, I need to do the same thing. I need to switch my Green's function for a regular one and my Robin's function for a regular one. So the idea is to use a Trenkenschein map, F epsilon, which has this form, is the identity, again, up to some threshold, which is basically ln of epsilon. And after that, it becomes a constant, okay? Okay, so that way, when you apply it on the Robin's function, then it has no singularity anymore. And for the Green's function, it's a little bit more complicated because, again, we need to make sure the singularities cannot compensate. Okay, so we have to split the truncation function and apply it on each term separately. Of course, this makes the study more complicated, but this is the only way we could make it work. Okay, because we proceeded like this, the system remains Hamiltonian because it is still the gradient perp of some smooth, this time, functions. So it's Hamiltonian and it has a global solution for every initial data. Okay, now the crucial part of the proof, what this works. This again was the idea of Marco and Pulveranti. We use the Chebyshev inequality. So if you introduce ST epsilon, the regularized dynamics, the one we will be working with, then if you fix one time tau, the probability of epsilon collapse is approximately so this is the Lebesgue measure. So it's the Lebesgue measure of the set of initial data that leads at one time between 0 and tau to the energy of the solution being big. How big? Being 1 over epsilon big. Okay, so we constructed everything so that this could be true. Okay, and this we now use the Chebyshev inequality, and this is controlled by epsilon times the mean energy, this integral on the supremum of the energy phi of the dynamic. Okay, so now the problem is considerably reduced because what we have to do is to prove that this term is bounded. If we can show that this term is bounded, then you have a probability of epsilon collapse that goes to 0 and epsilon goes to 0. Okay, so the probability of collapse, which is 0 collapse, will be 0 when taking the right intersection of epsilon going to 0. Okay, so what remains is to bound this energy. Since the system is Hamiltonian, this is very good because thanks to the Liouville theorem, we can remove the time from this bound. So this is a technical part that I have not included, but just to explain quickly, the area of the dynamics preserve the area during the time. That's the Liouville theorem. So you can all simplify to a problem at the time 0. And what does it mean? It means that you can reduce the problem to some geometric inequalities that doesn't depend on time, doesn't depend on the dynamic at all, actually. Okay, so now it's just a analysis problem on the domain omega. You have to prove that those two particular estimates are true. And you have just to prove that they are finite, actually, these integrals. Okay, so this is what Marco and Pulveranti first did in the case of the unit disk. They could do that because in the case of the unit disk, all functions are explicit. So they simply, if I may say, did the computations and proved that this is true. And in the case of general the domains, we have to extend those formulas. So how do we do this? First step is to use conformal maps to extend these inequalities from the unit disk to simply connected domains. Okay, the Green's function are very nicely transported by conformal maps, but this is a very efficient tool to transport those inequalities. And to have sufficient regularities on the conformal maps, this is where we need the assumption that the boundary of omega must be C2 alpha. Okay, then we prove that the same inequality holds true for the exterior of the unit disk. And then again, we use conformal maps to go from the exterior of the unit disk to the exterior of any simply connected domain. And at the end, we gather everything using some elliptical analysis to prove it for general bounded domain. So I will finish by drawing this proof, drawing something to understand properly. The idea is that if you take a domain with any numbers of holes, when you are close, when you have a point close to the boundary, which is the case when you have a singularity, actually the Green's function looks like the Green's function of the domain without the holes. Okay, so if you can prove it for the domain without the holes, then the difference with the case with the holes will be something bounded. And since we only have to show that some integral is finite, a bounded quantity is not a problem here. Okay, so this is how we do. We say if we are close to this boundary, we looks like domain without holes, and this we deal with it with conformal maps. If we are close to an inside boundary, well, it looks like the domains without the other boundaries. So this time is the exterior of some simply connected domains. Again, we deal with it with conformal maps. And the in-between doesn't causes any problems since in here there are no singularities of the Green function. Okay, so this is at least for the problems caused by the boundary. Of course, there is the singularity of the Green's function, but that's the most technical and important parts and my particular contribution to this problem. Okay, so what we saw here is that even in the presence of a more complicated boundary and not necessarily simply connected, which was the hard part, the point vortex dynamics has a global solution for almost every initial data. And I thank you very much for your attention.
Thank you very much, Martin, for your very, very nice talk. I think that by now everybody should be able to unmute their microphones if they do have questions or comments for our speaker. Or if you prefer, you can write down your question or comment on the chat, and then we will read it aloud. Are there questions or comments, please? I do have one question. Would it be reasonable to carry over the same techniques and methods for proving the same results, say for the upper hemisphere of a sphere with the boundary being the equator?
Yes, completely. Because if you study the upper sphere, you know that the Green's function is some modified version of the Green's function, because you can, again, via conformal maps, I think, take the upper sphere and put it in the plane. So this probably works. I wouldn't know the details right now, but when you deal with bounded domain on the sphere, it should work probably nicely, I would say. Of course, I'm not sure of that, but yes, it's reasonable to think that it would work.
I see. I see. Do we have questions or comments for Martin? If we do not, then we thank the speaker again for his very nice talk. Thanks a lot.
Thank you very much.
You're welcome. It is now 11:50. Our next local time. Our next talk starts, if I'm not wrong, 1:10 in the afternoon. So it is an hour and 20 minutes from now. So we will be back at that time with a new talk. All right. So thank you very much for being here this morning. And let's meet again an hour and 20 minutes from now. Thank you very much.